Please give a round of applause to Dr. Maximilian.
Well, thank you all for your kind attention. So, as introduced, I'm Max Bernbeck. Just to give a little bit of a brief background on where I'm from. So, I was born in Southern California, decided to move up the coast to go ahead and get my bachelor's degree for Professor John Arnold, one of the small molecule inorganic founders almost. Was really lucky for that. Decided to move down to San Diego for my PhD. Nice and sunny down there. Got to work on some interesting magnetic molecules that I'll tell you a little bit about with Professor Jeff Reinhardt. And then I figured, well, West Coast, best coast as it may be, is a little bit limiting. So I decided to drive all the way across the country, start working for Professor LaPierre over here. Professor LaPierre is the one who owns this instrument. So what kind of work did I do? Well, so when I'm talking about small molecules, I specifically work on inorganic molecules. That is any organometallic molecules, anything that's a metal bound to any number of either carbon-based or other ligands, ligands being things we bind to our metal centers, such that we can go ahead and design things for various purposes. So for example, in John Arnold's group, I work on this titanium system for the purpose of building catalysts. Well, that's at least what we put in our grants. For really, we just did it because chemistry is cool and we wanted to see what we could make. Moving over to San Diego, I decided to move into single molecule magnetism, where I worked with lanthanides, which there's not a periodic table number for some reason. But if you know those two little detached rows at the bottom, those actually make for some really interesting single molecules that can behave like magnets for certain periods of time. And actually, what I'm showing here is a crystal structure from one of my structures right before I graduated that we got using one of our diffractometers. Moving over here, I now work with uranium actually in making these tetrahedral molecules for the purpose of making qubits. I don't know how much you've heard about qubits, but basically, if you want to boil it down to the smallest bit, it's if you take a computer bit, you throw a quantum on it, you can call it a qubit. What does that mean? No one really knows right now. I'm trying to figure out, but it makes for some excellent science where we can hopefully push technology a little bit further. But as you can see here, I have a couple of crystal structures. Where do we actually get these? Well, like Susanna mentioned, I help run the crystallography facility here alongside two fantastic scientists, Dr. Julie Nicholas and Caitlin Ott, who are both also, Dr. Julie Nicholas is a research scientist and Caitlin Ott is a graduate student working for Professor LaPierre. And this is actually something called we have a name for it, it's Carl. It's our D8 Venture instrument. Where we can use both copper and molybdenum X-ray sources, I'll get into that in a second, to be able to get the structure of these small molecules. So what is so useful about crystallography? Well, it's an extremely versatile tool for being able to get structural information. So for example, we have what I'm going to talk about today, which is mostly single crystal diffraction, which can get us to very high level of precision, our structural details. You can see here, this is a diffraction pattern. This is just one frame of a diffraction pattern that shows just these little spots. When you go ahead and grab a whole bunch of these images and you do a copious amount of math, you can go ahead and get this structure out of that, which is pretty neat. Another thing is, well, if you don't happen to have a nice single crystal, there's actually also a useful technique called powder diffraction. I'll touch on that a little bit there, where we can instead get kind of a bulk view of a crystal. Think of this as like kind of like an NMR or any other experiment where you're looking at a bulk sample rather than trying to look at a single crystal. And from these diffraction experiments, we can look for data at a variety of resolutions. So if we just need, for example, a general shape of a molecule, we go ahead and go out to a pretty low resolution and we get that pretty well. Or if we decide to shoot it with the best X-rays we have and get fantastic data, we can go ahead and see individual atoms in our molecules and be able to build them from there. Now, X-rays actually aren't the only tool we have available to us. They're the only tool we have available to us here at Georgia Tech. But there's also neutron diffraction. So X-ray crystallography, like I'll talk about, X-rays interact with electrons. Unfortunately, some atoms' electrons are much better or much worse at being able to scatter X-rays than others. So from that, we can instead go to neutrons. Neutrons instead scatter from nuclei. They're the right, so whereas X-rays are the right wavelength to interact with an electron, neutrons are the right wavelength to be able to interact with a nucleus. Unfortunately, though, we're really limited in where we can do this. Really, you can only get this done at a national lab, somewhere like Los Alamos or Sandia or somewhere like that. I think Oak Ridge is currently the best. That means nothing, I guess. There's also electron diffraction, which is actually a relatively new technique. It's very interesting. People are using this to complement X-ray crystallography because, interesting enough, these are charged particles, so they can interact with the nucleus pretty well, but they're also at a short enough wavelength that you can interact with the with electrons quite nicely too. So you can see you get really high resolution. However, this is still a relatively new technique, and so not a lot of people have this capability. So let's go ahead and focus on X-ray crystallography for now. What can we get from this? Well, let's go take a look at a typical structure. This is one of the molecules I've collected while I'm here at Georgia Tech. We can, first of all, just get our atom positions. Where are atoms in the crystal? This will tell us generally the shape of our structure. But in addition to where the atom positions are, we can also tell the different atom positions diffract slightly differently. So this tells us the atom identity. You can see many different colors on this scheme here. For example, we have orange for phosphorus, blue for nitrogen, black for carbon, and we can tell to very good precision what the difference between these atoms are. And this is really helpful for being able to tell us the difference between, oh, do we have something like ethene or do we have methanol? Because those are really different molecules. And so being able to tell the difference between those is very helpful. Another one is something called thermal parameters. You'll notice these aren't just little spheres here or points in space. They're these kind of spread out ellipsoids. That's because atoms in a solid, they're not perfect. Even though this is sitting here nice and soft on the table, all the atoms in here are constantly vibrating and moving around. Similarly, in a crystal, they're also constantly vibrating and moving around. Depending on the temperature you take your crystal at, you can see the uncertainty that you have for each atom position. So for example, at some point in time, this atom might be all the way here at this extreme of the ellipsoid, might be all the way here at this extreme of the ellipsoid. Now you can tell that's still a pretty narrow range of positions that it can be in, but it still gives us some information about how that crystal or how that molecule is wiggling around in that crystal. And lastly, there's a whole bunch of other things you can pull out in more niche experiments. So for example, if you've been taking organic chemistry or introduced to the concept of chiral molecules, these are molecules that have a certain handedness that aren't related by a mirror. That can be really important to be able to tell, especially considering one version of a chiral molecule will cure cancer and the other version of the chiral molecule will kill you. And so being able to tell what those tell those apart and whether or not you have purely one version or the other is very important. Similarly, we can tell how the crystal expands or contracts based on the temperature we run the experiment at. And honestly, some of the most important stuff, for example, for magnetism is being able to tell, okay, if we have a single crystal, if I point that crystal in a certain direction, how are the molecules pointed? So where in a regular experiment, sure, I just get a structure out of that, but say I keep that crystal. Now I know when I align that crystal, how am I aligning the molecules in that crystal, which could be very important for certain experiments where that alignment really matters. Okay, let's take a step back. I said I'm a small molecule chemist, and I tend to work with these small molecules, not with proteins. So what is a typical day for a synthetic chemist getting to the diffractometer? Well, first of all, we have molecular synthesis. This is typical for most other labs. I mean, we're using the same glassware as in a biochem chem lab. It's just we're working with a lot smaller stuff and tends to be a lot more colorful. I'm biased to inorganic chemistry. It's really nice like that. A lot of my reactions are pink, orange, and purple. And it's really nice. Then I go ahead and take this product and I really purify it. Purification is key for being able to get good crystals for crystallography. Like I'm going to be talking about in a second, being able to have very pure crystals is important such that your structure actually represents that single molecule you're trying to look for and not just some agglomeration of multiple together. That's actually typically going to make it so that your crystal is completely unusable for diffraction experiment. You're not going to get useful data out. But so after you purify it, you still need crystals of it. If you have a really pure oil, that's not going to be really useful to be able to put onto a diffractometer. So we go ahead and crystallize it. These are some crystals that I went ahead and took a picture of for my box. They don't look that nice, unfortunately, because while they're really nice and beautiful pink to the eye, once you go ahead and take a picture of it, they actually fluoresce a little bit, and so they look like it's kind of dull purple. But you get some nice crystals. You go ahead and throw it onto this tiny little nylon loop and go ahead and get your diffraction data. All right, so this step, crystallization. I'm not going to go too deep into this because you have a whole workshop on it today. But just to give a little bit of an idea, we use a lot of the same techniques that protein crystallographers use. One thing that we like to take advantage of is thermal equilibrium. This can either be by just taking a solution that we have already supersaturated it, lowering the temperature, and your solubility of whatever's in the solution is going to decrease. You'll slowly get nice crystals growing. Now, if you can't supersaturate it before you throw it in the freezer, well, maybe you can get it to saturate while it's in the freezer. So another thing you can do is go ahead and take your solution, slowly evaporate out your solvent such that it gets more and more and more concentrated until you start getting crystals coming out once you reach the solubility limit. Now, another thing is, say if this one solvent isn't doing it and you're not able to get it to a high enough concentration where it's just going to fall out, well, maybe you can dilute the sample with a solvent that it's not soluble in. That's where you get diffusion experiments, both vapor diffusion, which is very slow. You're waiting for this vapor to be able to evaporate over into your smaller vial. And what this does, say, for example, I have something that is soluble in water, but it's not soluble in methanol. You can think of methanol, if you think about the fact that you can smell it, it's very volatile. It likes to evaporate a lot faster than water. So if I go ahead and take a vial of my crystal in water, or of my compound in water, and I slowly diffuse in methanol, if it's not soluble in methanol, that solution is going to end up becoming more and more and more methanol. Eventually, you're going to reach a mixture of your methanol and water that your compound isn't soluble anymore. Start getting crystals. And if you're impatient, you can't quite wait for that to diffuse over, then you can just go ahead and throw all your liquid on top of each other, hoping that it diffuses slow enough that you get crystals. That's for liquid-liquid diffusion. So what kind of crystals are we looking for? Well, thanks to my wonderful colleague, Andrew, I got these nice ones to show you. You want to get a nice single domain crystal. When I'm talking about, you can see that this crystal all kind of looks like just one nice continuous piece. We call it a domain without it breaking up into different parts that are grown together at different angles. This will typically give us the best crystallography. I'll justify that in a second. Well, actually, let me justify it now. So we talk about these big crystals, but what are we looking for? Well, we're looking for periodicity. We want to see that a crystal is basically one repeating unit. Think of it as just a box with your molecule in it. If you go ahead and shift that box over by a regular amount every time, you're going to see that same molecule oriented in that same direction, same distance between them. So this is what ends up making something called a lattice. So I have this nice, you can actually get something, you can get 1D crystal, one-dimensional crystals and two-dimensional crystals as well, just to kind of ease yourself into thinking about it in 3D. So I have this nice M.C. Escher painting here. He really liked building lattices. And so if we go ahead and draw a line from the tip of each of these white geese's beaks to each other, you'll end up seeing that in this box, we have one blue goose and one white goose. Now, unfortunately, the white goose has been kind of split in half. It's an unfortunate thing. He'll sleep it off. But you can see that if I go ahead and shift this over here, this beak over here fills in over here, the rest of the bird, and I end up having one blue bird and one white bird again. And this is entirely dependent on how you want to define your unit cell. Many different unit cells can be valid just as long as you're trying to choose the smallest repeating unit possible to describe your crystal. So, as you might imagine, you would want this periodicity to not be broken by, let's say we took one of these birds and rotated it 90 degrees. Well, is there any other way to move that bird such that it overlaps with another bird there? Looking for audience engagement. No, right? Like if I go ahead and take a 90-degree flip bird, there's no way that I can just move that bird around to make it lie on top of another one of these birds. And so if I have, for example, crystals that are grown at 90 degrees from each other, that's just like this bird here. Crystal 1 that's grown at 90 degrees to crystal 2, I can't get that just by moving it to overlap with the second crystal. So we're looking for, bless you, a repeating unit here. What does this look like for crystals? Well, these are the unit cells for crystals. It's a little bit less fun to look at than birds. But you can see here we have many different types of unit cells. Now, the unit cell I showed you before, this is something called a primitive unit cell. This is something where in each unit cell, you only have one bird. You have 4 corners here, and you can think of it as each of these corners marked by the location of, for example, a beak is a lattice point. Now, there's many other different types too. So you can see we have those primitive cells again, where we only have the corners being matched by what's in the unit cell, but we also have different types of centering. This just makes it, these are just different ways to represent similar crystals in ways that are a little bit simpler. It gives us a smaller, more contained repeating unit that matches nicely with symmetry. So, for example, if I go ahead and take this simple unit cell, this is a simple cube. This has 8 lattice points sitting around on the 4 corners. And if you think of each of those lattice points as having a sphere, right? each of those spheres is going to be cut into eighths by those corners, right? Think of a box at the corner. If you have a sphere at the corner of that, only 1/8 of that sphere is going to be inside the box, right? So if we go ahead and take all these 8 corners, even though we have 8 lattice points on this cube, this represents 1 molecule, 1 total lattice point. And so this represents the simplest possible unit we can build in order to take our 1 repeating unit and then across. Now, in body-centered, for example, now we have our 8 corners. That's 1 lattice point again. But now we have 1 that's completely inside. We have 1 sphere that's in the box. So now with 8 1/8 of a sphere and 1 full sphere, we have 2. And so this ends up giving us different ways that we can describe the symmetry in our system. Now, is there more symmetry than this? Just being able to do translational symmetry? Well, yeah, there's a lot of different things. So for example, we can have rotation. We go ahead and take 2 different neighboring cells. Let's say we have a molecule Q at this location here. You can see that each of these points here is represented with an oval. That's something called a symmetry element. This one right here represents a 2-fold rotation axis. This means that if I go ahead and take my what's something with symmetry over here. If I go ahead and take, for example, this roll here, 2-fold symmetry operation means if I go ahead and forget the fact that this like winds in different directions, but if I go ahead and rotate this, you can't really tell apart whether it's pointing up or pointing down, right? This is a roll either way. So similarly, if I have a molecule here and a molecule here, related by this 2-fold rotation, those 2 molecules are going to look identical. They're only different by their positions. So you can see that again, these repeating units can be matched by higher levels of symmetry. So this lets us actually interpret things a little bit easier. Say we have those diffraction patterns. Well, if those particular spots represent certain atoms in there and we have symmetry across our diffraction pattern, then we can tell, hey, this point is supposed to look like this point. And so we can use that as constraint to be able to tell us our information. So unfortunately, this was the slide that I had to fix because I actually grabbed the wrong image. But let's go ahead and do a really quick experiment here. Let's take this fictitious space group right here. Let's go ahead and build up what this would look like. This is something called an orthographic projection. This basically tells us, okay, so if we have some object here, how does this transform with the symmetry of the unit cell? So this, for example, is a 2-fold axis here. And we have a lot of different notation here. So for example, we have the circle and the circle with a little comma that tells us handedness. So for example, we could say the open circle is like something that looks like it's right-handed, something with a comma in it, something that looks like it's left-handed. You can see that these 2 different projections are related by if you had an invisible mirror here, you went ahead and mirrored my hand through here, you would get from my right hand to my left hand. Similarly, if you took a mirror, you would go from your open circle to your comma circle. And the plus and minus just represents whether it's above or below the page. This is 3D space that we're looking at here, so it's kind of hard to think about it in a 2D plane, so we do our best. So, thank goodness Zoom has annotation, because now I can go ahead and say, wait, does it have annotation? Okay, PowerPoint should have it. And then, let's see. Please, let me draw. Maybe. Do you know if Zoom still does annotation?
Should have.
Huh. Okay, well, sorry to those who are eventually watching this in the future, if you are, but let's go ahead and do this by hand then. Let's see here. Okay. So, I'm going to erase this. Now I have access to the whiteboard instead. Well, ain't that convenient? Okay. So I'll just have to point it out. If I go ahead and take this circle here, this is a 2-fold rotation. Someone tell me where you think this is going to go ahead and hit that. Right here? Yeah. So this circle, if I go ahead and rotate this about this axis, we're going to end up with a circle, open circle, plus right here. Okay. So from there, we also have a mirror plane. So where do you think that we're going to end up with the circle next? Is the position going to move at all if the mirror plane is in the screen? Like, is it going to move at all left to right, up, down? No, I saw some shaking heads. Instead, it's going to go below the plane. It's basically going to be superimposed with this circle right here. But it's just, if you think about this as being a plane here, this circle starts up here. We're moving the circles down here. Now, is that going to keep the same handedness? It's a mirror, right? So what happens with mirrors? Flips, right? We're going to have a comma below. And from that, now we've only built 2 positions here, but from that, we can go ahead and build out the rest of the positions on it. So for example, now that we have a second circle here that's facing the opposite direction, well, that also follows the 2-fold rotation. So we're going to put another circle down here. You can also do that in the opposite order. Start with the one above the page, do a 2-fold rotation, and then do the mirror. You end up in the same spot. So all of these symmetry elements work in tandem to go ahead and build you the bigger picture of what's going on in your crystal. Okay, but I've thrown a whole bunch of math at you. Let's go ahead and finish that off with with the actual math. So if you, I don't know about Gen Chem here at Georgia Tech, but you might have been introduced to the idea of Bragg's law. Does anyone remember that? It was really used as kind of like a kind of hand-wavy way to describe, like, oh, if you have a bunch of planes, you go ahead and reflect light off of it. You can describe how that interference, because light, wave particle duality, it's going to act like a particle and then it's going to bounce in the straight line, but it's going to act like a wave such that these 2 different light particles are going to interact either with constructive interference, or the 2 wave amplitudes will add, or destructive interference, where they'll subtract from each other, or somewhere in between, if it's not at a perfect interval of constructive or destructive interference. Now, in Gen Chem, you might have been described this just, with general planes, but we can describe this with a lattice too. So if we have a whole bunch of lattice points here, so let's go ahead and think of these 4. If I'm going to go ahead and look from this direction, this looks like a plane, doesn't it? So similarly to how, actually pretty much exactly like Bragg's law describes, we can think of these different lattice points as planes that our light is bouncing off of. It just depends on what our frame of reference is. And from that, we're going to build different diffraction patterns. These lights, so let's think of these as our 2 different planes. These different wavefronts are going to go ahead and add constructively or destructively in order to build our diffraction pattern. So where these overlap constructively, that's where we get the spots that I showed you earlier. Where these go ahead and add up such that they completely cancel out, well, that's all the dark space you see in a diffraction experiment. And depending on what your crystal looks like with your grading, you can get a whole bunch of different diffraction patterns that tell you a whole bunch about how your atoms are arranged in your unit cell. So that's a lot about what kind of data we're getting. What's the actual experiment you're running when you go ahead and go to a diffractometer? Well, let's go ahead and look into what kind of X-rays we're using. Why are we using X-rays in the first place? So when we're generating X-rays, we're really trying to take advantage of electronic energy levels. So for example, if you go ahead and excite an electron out of your lowest energy level out just 1, so let's say if you remember your different transitions from, I think, Gen Chem or Gen Chem Lab, you go ahead, you have your Palmer series, your Paschen series, your Lyman series. These all describe different shells that you can bounce between in order to get X-rays. So for example, if you go from n+1 down to n, say you're going from your 2p down to your 1s, that will give you alpha radiation, kappa alpha radiation. K describing you're going down to the lowest energy level, and alpha meaning it's the first one. We're not really that imaginative. And then we have, further on L alpha, but the most consistent one that we can get is kappa alpha, you imagine, right? It's the most common one that you're going to go to. Most electrons will want to go down to that lowest energy level. So unfortunately, though, this is typically going to give us something called just white radiation. We're going to get X-rays at all different points because we have all of these different things, not only adding together those specific energy levels, but you also get imperfect interactions with your electrons, except for a couple of features here. So you see this continuous radiation associated with our X-rays, and then there's a couple of spikes that are associated with the actual excitations that we're doing. And we can take advantage of different specific targets having very specific energy levels. So for example, two of the most common sources of X-rays you're going to see are copper and molybdenum. Copper and molybdenum have very nicely described kappa alpha and kappa beta, this kappa alpha and kappa beta emission spectra. So we can expect very nicely what those are going to be. Very high intensity, so they're much more intense than the white radiation, as well as nicely spaced. And that nicely spaced is really important because we need to be able to filter out the light. So for example, if I go ahead and throw a zirconium foil on molybdenum, it's going to block out all this kappa beta radiation, and now I have a single wavelength of light, kappa alpha. And that's going to be really important because if you remember from Bragg's equation, you want one wavelength. You need something monochromatic. So this allows us to have some monochromatic X-rays of very high intensity that we can use. How do we make these? Well, we have a couple different designs, but generally you just shoot electrons at a metal and then X-rays come off. Now, you need to do a little bit to focus that. Otherwise, you're just going to get nice dose of like 300 bananas per second. But if you go ahead and throw this into an evacuated tube and then focus all of your light towards one useful X-ray beam, then you get a very nice beam. Unfortunately, though, this tends to melt the target because electrons are hot. And so if you don't have very good cooling, this can melt. And so we've gone ahead and crystallographers developed something called a rotating anode, where we can take this molybdenum disc, spin it around, hit it with electrons, and then by the time that it's going to get hot enough to melt, it has rotated out of the electron beam, so it's not going to get hot anymore. Then it cools off, comes back around, and you can go ahead and build more electrons. Well, that's great. But how do we, X-rays aren't that useful if after we shoot it at a crystal, we have no way of measuring. So what do our detectors look like? Well, one type is called a photomultiplier. This is where you take, the X-rays that come out of a crystal, even after they've interacted with the crystal, are extremely high energy. So if you go ahead, once it's gone ahead and hit your detector at a specific pixel, it goes ahead and interacts with the material inside to emit more photons of lower energy light. So let's say, for example, this electron hits this X-ray hits here, gets you blue light, green light, yellow light, red light, and you multiply your photons each time because you need to conserve your energy. So if you hit a longer wavelength of light, lower energy, you're going to get a lot more out. And so whereas here, the X-ray that came in, say you measured one X-ray, by the time you get down to the end of the tube, you can have hundreds of photons and increase the intensity of your signal by a ton. Now, that's just one type. What's more common nowadays is something called a charge-coupled detector, a CCD, where you go ahead and have your radiation go and hit your metal target. What this does is it shoots off an electron, or it at least separates the electron from its host in the detector. And then after a certain amount of time, because you have very defined exposure times that you go ahead and shoot your X-ray at your target, you then go ahead and pass a charge through it and read out where all of your different charges are. This tells you which pixels that X-rays have hit, and again, gives you a good picture of where your X-rays have been diffracted. Now, I've been using that term a lot, diffracted. I know we're kind of bouncing all over the place, but so I'm talking about, all right, we shot the X-rays. Okay, we measured the X-rays. What happens in between? Well, that's where the real fun stuff happens. We have two things that give us information and one that takes us away. One thing is elastic scattering. Elastic scattering being where once your X-ray hits your target, so for example, the atom in your crystal, it's going to bounce off and maintain all of its energy, something called elastic scattering. Think of this as basically an elastic collision from your intro physics class. You take a rubber ball and you bounce it off the wall and it comes back at the exact same speed. That's what's happening with this X-ray. Goes ahead, hits your atom, comes off at a very predictable angle, 2 theta, the same one from the Bragg equation that we had before, and keeps all of its energy. Now, inelastic scattering is a little bit more wishy-washy because now this has interacted with your electron, not a perfect sphere anymore. Atoms have these weird spread out orbitals, and so it can absorb a little bit of that energy and deflect it at a random angle slightly off from 2 theta. This is why this is actually a little bit good, because if you remember, we have these spots. If we only had elastic scattering, we would have infinitely tall single pixels and be pretty much unable to measure them. This gives some imperfection to our measurements. This is how we get the nice round spots that that I showed you at the beginning, and I'll show you again in a second, that lets us actually measure our reflections. But of course, they come off with a little bit less energy and a little bit different angles. This adds some uncertainty into our measurement. And lastly, there is absorption. There's many different ways by which the crystal can absorb it. For example, the photoelectric effect I was showing you earlier, where you go ahead, shoot in an X-ray, you excite up your electron, it comes back down, and you go ahead and emit light off again. Typically, this looks like it's just gone straight through the sample, but that emitted light can go off in any direction. Similarly, if you don't get that nice perfect absorption, you get somewhere in between, then you can just lose the energy of that light. But we typically have to correct for these in our experiments. Now, I was showing you that angle 2 theta. Well, why aren't we just getting spots everywhere then? Well, we could only measure certain spots at a time. And this allows us to do many different reflections in order to be able to get the entire picture. So for example, if I go ahead, say A is my source here, C is my crystal, and then N, O are on my detector. We have this circle that measures exactly where constructive interference is going to give us spots, destructive interference is going to give us nothing, and everything in between is also going to give us nothing. And so only on the surface of this sphere are we going to see our X-rays that come out actually hit our detector. And so say, for example, on this one, we're only going to be able to see maybe 1, 2, 3, 4 spots. But we can move our sphere. That's what 2 theta is all about. So we use something called a goniometer to move our crystal around. And so from that, once we move our 2 theta, move our distance, change the orientation of our crystals, we move that sphere all around such that we hit every single spot in that lattice. And once we've hit every spot in that lattice, well, now we have a complete picture of all the atoms that scattered and caused that. So this is something called a goniometer. It's 2 different designs here. This is something called Euler's cradle, nice and fancy. This is the one we really use, which is the 3-axis, where we can go ahead and change our 2 theta. So we see here's our source coming in and our detector. We can change the angle that our crystal is relative to the detector with 2 theta. We can also move our crystal up and around in all different orientations such that we're seeing every different type of Bragg plane orientation. And so from that, we can go ahead and instead of that one picture I showed you before, we can get an entire smattering of frames. So for example, I'm going to show you one of my experiments here real quick. If it's going to let me, it's going to be able to. I think I silenced it because it's really loud in the lab. Huh. It's not letting me play it. That's odd. Huh. I need to try restarting presentation there. Oh. Zoom. Share screen. PowerPoint. Share. See if it works. Nope. That's sad. That's what I did. Well, I'll show you on here. Let me just go ahead. I'm going to switch Zoom to just screen 2. Yeah, because I'm just going to go ahead and share the screen again, just so the people on Zoom can see this. If I go ahead and go to screen 2, so if we go ahead and take images in many different orientations, we see these spots move around as they pass through our sphere. And so we can collect hundreds, if not thousands of frames to be able to get every single, oh yeah, thank you. Yeah. And all of these different spots represent some constructive interference of different exiting X-rays interacting with each other. And so, get back on the Zoom again. And so now we have a lot of control over our experiment. Okay, so now let me walk through. So we've talked about where do we get our X-rays from? What do they hit? What's the symmetry of our crystal going to give us? Well, if you do a modern X-ray experiment, most people who do these never have to think about that. They either hand it off to a crystallographer, we go ahead and take care of it for them, or they go on there, and for the most part, the program takes care of all that math for us. It's just very good to be aware of. So what actually happens? Well, I've gone ahead and just to wrap up most of it, I've got one of my own crystals that I collected back in grad school that I decided to resolve and show you the different steps of. So we start off, nice blank canvas, we have all of our data. First things first is this is going to tell us how good our data was before we even start working with it. So this tells us, okay, this is something called R internal. This tells us, okay, the model that we use to describe where the points are in 3D space match up really nicely with the experiment. I over sigma. This is called our signal to noise ratio. This is basically telling us, okay, our peaks are on average 50 times as high as the noise. Good. This tells us that our peaks are real and not just different, like little random peaks that we decided to pick out. The resolution of how closely, like how well we can see with our X-rays. So, for example, this 0.8 says that we got resolution up to 0.8 angstroms, meaning we could tell within every 0.8 angstrom interval very well what the where the spots were. And while 0.8 angstrom doesn't sound a lot, especially for bonds that are on the order of 1 angstrom, this can actually get us a precision down to like 1/10,000th of an angstrom. So that resolution can be a little bit misleading. So let's go ahead and hit the solve button. We're going to get a nice, beautiful, complete. So that's not a molecule. That's a mess. But we can already see a little bit of what's going on. So we can see we have different radii going on in spheres here. Generally, you can tell that the radius of the sphere tells you how good it matches up with that atom. So for example, all these nice small carbons and oxygens, those match up pretty well with oxygens and carbons being there. This is a metal called erbium. That matches really well with being there. Typically, your heaviest atom is going to be the most precise because that matches up with your highest intensity peaks. And we can also take a look at, okay, if we go ahead and refine this, what does it look like? Well, now we also have something called Q peaks. Now, these Q peaks represent electron density because, I may have forgotten to mention before, but since X-rays are interacting with your electron density, this represents electron density that has not yet been accounted for. So all of these atoms are accounting for a certain amount of electron density in our crystal. And all these Q peaks say, hey, what about here? Why didn't you model anything over here? And so now we go through the different steps. First thing I do is I go ahead and delete a lot of the way too big atoms. We go ahead and take a look here. This is another representation. You can see these Q peaks overlap a lot with these green spheres. This actually represents the leftover electron density in our unit cell. So green spheres represent positive electron density, aka actual electrons that we haven't dealt with. Red spheres represent negative electron density, or this means that we've overmodeled. We put something there that represents more electrons than it should for that region of space. So then I go ahead and go through and start taking care of the structure. Now this requires a certain level. This is why it's kind of this weird thing where crystallography is a very specialized skill, but you typically use it as a tool alongside of your other stuff because you need to have some level of chemical intuition to be able to build this from here. So I go ahead and delete a lot of large atoms and I go ahead and build in the structure. And this is starting to look a little bit more like a molecule, right? So this erbium atom is now bound to this ring down here, although that ring is pretty messed up. It's also bound to a couple more atoms here that look like they're building a molecular structure, but this obviously needs a lot more work. And so I go in, over a few more refinement cycles, we see a couple more big spheres pop up. Go ahead and delete those. We have more Q peaks that represent unlabeled electron density. So we put atoms there. So for example, on a couple of these larger ones, I'll say, oh, that's supposed to be a carbon, or this is supposed to be an oxygen. And then we finally get an actual molecular structure. So we see here, this is some erbium that's bound to these two oxygen-containing rings and a benzene ring with a methyl group on there, which is pretty neat. But this still isn't complete. Where are the hydrogen atoms? Well, we can go ahead. Unfortunately, hydrogen is really small. How many electrons does it have? One. Carbon has 6 times as many electrons. Erbium has 60 times as many electrons. It is really hard to see hydrogens in crystal structures. Typically, you have to go to neutron diffraction to see those. So what we do here is we just model them. We go ahead and say where they should be. We do a lot of complicated math because not only does it only have 1 electron, but that hydrogen electron doesn't even stay around the hydrogen nucleus, right? When a hydrogen bonds to an atom, it goes into the bond. That bond sits in between. If I went ahead and said that all the electron density around here should belong to a hydrogen atom, they would all be super short, like right next to the carbon atoms. So we instead use a model, and through this we can describe, okay, this is a reasonable description of the hydrogens. We use a little bit of math to say, okay, if the electron density is here, then the hydrogen should be a little bit further out, and then thankfully someone else has figured that out, so I can just press the button in the program and it gives me the nice structure. But the last thing is, remember I told you before that, okay, we want atom positions, we want atom identities, but thermal parameters are important too. We want to be able to say, okay, these are these atoms this percentage of the time, and also like this actually represents a reasonable atom. So I go ahead and throw in something called anisotropic refinement. So whereas before they were just positions, and they were said, okay, they have some like probability of being out this radius. Now we've gone ahead and say, okay, this matches, it can go up and down this axis a certain amount, but less in these 2 axes, and we get the thermal parameters for this crystal. Now we have a nice complete structure of one of the last things I published for grad school. So yeah, that's the general gist of a single crystal experiment. Now, there's just a couple more things I mentioned really briefly. Powder diffraction. Now, this actually builds off from the same principles of single crystals. So think instead of a single crystal being mounted and you rotating it through every possible angle. Well, what if you could get every angle at the same time? So if you go ahead and take a powder and throw that on to a diffraction experiment, you can think of those as many, many, many different microcrystallites that are oriented in every possible orientation in space. And so you're just going to get every spot at the same time. Now, while that's kind of useful for being able to get a fingerprint, now they're all overlapping, and now we can't really tell the atoms apart. But this is really useful for a diagnostic perspective. So the sphere that I talked about before, instead of seeing those individual points, now we've gone ahead and taken those points and rotated them through every possible orientation in space. And now you can think of them as, so if I go ahead, think of the grid that I showed you before here. I rotate that 1 degree, rotate that 1 degree again, and again and again. And you'll eventually see that all those spots smear out into these circles, similarly to the shells over here on the sphere. And so from that, we get something that we can use as a fingerprint. So instead of being able to see, okay, this is what the atom positions are, we say, okay, if this structure is what we think it is, this is what the powder diffraction pattern should look like. We can go ahead and match that. So instead of running an entire experiment, we can do just a really quick one within an hour. For example, this was actually one of mine that I went ahead and took. You can calculate what the diffraction pattern is supposed to look like. That's what the black lines are. And the red lines are the actual diffraction pattern. You can say, okay, do these peaks line up? If yes, cool. Most of my material is A, crystalline, and B, clean, which is really nice. Lastly, something I know very little about relative to small molecules is protein crystallography, but they follow the same basic principles. It's just a lot more difficult because proteins, A, they're huge, so it's hard to get them to bend in a periodic way. So for example, protein A and protein B right next to each other can fold completely differently. And so to get those to actually crystallize is very difficult. You have a lot of atoms in there, so they absorb a lot. But you can get some beautiful diffraction patterns. And thankfully, even though you can't get the highest resolution, you don't need that because you don't care about where the individual atoms are for the most part. There are some very specialized groups that are trying to be able to see what those individual atoms are doing. But for most protein chemists, they really just care about the folding, your alpha helices, your beta pleated sheets, and you can get that from really low resolution crystallographic data. So it's very useful for those purposes too. So just want to wrap up with a really quick summary. I hope you see that, okay, there's a lot of math behind it, but crystallography has a lot of different knobs and levers that you can pull and twist in order to get the type of data that you really need. But you should really be thinking about these because while you grow a really great crystal, I have seen some fantastic crystals give absolutely awful diffraction patterns because people mishandled them or put them on wrong or didn't quite use the right parameters, such that even though their data would have been pristine, the way they collected it made it absolutely useless. So you need to be really careful in the kind of choices you take there. And lastly, something I didn't really get to go over in the presentation, but being able to learn all this, the background is really accessible. So you might be able to get from Susanna in the future. You have already been looking through it. The Girolami textbook is actually extremely cheap, as well as most of the learning material that I provided today, you can find for free online. There's a ton of resources online for being able to get people into crystallography. So with that, I want to thank you so much for your time and take any questions.
So you had the different steps in your project example with like the different spheres and Q spheres and all that.
Yeah.
How long of a time frame does that actually take?
It really depends on the crystal. I have taken an entire, like several afternoons to solve particularly difficult structures. So I chose a structure that was really well behaved, but there's actually a lot of different things that can complicate it. So for example, I told you we want single crystals. Well, sometimes life just doesn't work out the way you want it to, and you have to deal with having multiple crystals grown together. So there's some things that you have to do to take care of that. Or for example, if you have these nice thermal ellipsoids, say that these atoms belong here like 100% of the time, pretty much. But there's some structures I've had where you have huge ellipsoids that are instead better modeled. Instead of saying, oh, this can wiggle this much, is instead, okay, 50% of the time the atom's here and 50% of the time the atom's here. There's a lot of complicated models. But for something like this, yeah, it's took about 5 minutes. To do the solution, the actual diffraction experiment can take anywhere from like an hour to several days, depending on the quality of your crystal.
You said like the molecules that are in the crystals actually always moving around, right?
Yeah.
How do you differentiate or looking at your diffraction data whether or not the structure you're looking at is the same orientation or if it's been moved around while you're getting data?
Oh, that's a really good question. Thankfully, even though they're constantly moving around, they're moving around very little relative to the extended structure. So if you go ahead, it's kind of a combination of, oh, they're wiggling around and neighboring will be a neighboring atom or neighboring molecules that should be identical or very slightly different because they've twitched a little bit. But if you go ahead and look over the entire crystal and you take like the average, you take like a statistical model, they're actually very well localized. Yeah. But sometimes it can be very different. I've had, again, like I was saying, I've had molecules where this thermal parameter is super wide. And so it ends up being that in the crystal, half the time it belongs in one position, half the time it belongs in the other. And the average of those two ends up looking like this really smeared out position. That's a great question.
But the unit cell were like each of the points like this simple out of that. So like all
that's an excellent question. So I was providing the unit cell as, oh, it's a single atom. It's kind of like a really simplified view. It really helps you to be able to take a look at it. Realistically, those lattice points should be entire molecules. And what ends up happening is you get, so if that was a single atom, say, for example, you had a metal crystal, because metal crystals are just 1/10 metal, then you can get, okay, this is supposed to be this density. When this comes off of it, this is that particular atom. But when it's a whole molecule, the waves are not the same length now. The way that it scatters off of one atom is slightly different than the other. So when I was talking about the total constructive interference or the total destructive interference, that really only happens when everything that it's bouncing off of are the exact same identity. But say if I have a neighboring, for example, carbon atom and a carbon atom and an aluminum atom, good enough like difference in their size. When they bounce off each other, the wavelengths are going to be different enough such that you get some interesting patterns that aren't completely constructive or completely destructive. It's something I didn't really want to put in the presentation because it gets a little into the weeds. It's a bit beyond like just like a seminar, but it's something called the phase problem. So I talked a lot about intensities. You get higher intensity when they overlap and lower intensity when they disrupt. But you also care about the phase because that tells you how far that path has moved and also like, so basically how far that electron has, that X-ray has moved, it tells you, okay, what's the path length, what's the identity of the atom, and you can't measure that directly. So there's a lot of math that goes into being able to, a lot of, if you've heard of them, Fourier transforms or Fourier transforms, if they pronounce it like that, to be able to back calculate what the original waves should have been once you have the final spot. But it's actually a very difficult, complicated problem. that people spent about a couple hundred years figuring, or about a couple decades figuring out, and then throwing it into a program so that none of us have to think about it. Yeah.
So I know for protein crystallography, to solve the phase problem, they use, for example, they replace one of the sulfurs with like a selenium
Mhm.
to enhance the signaling. So if you're dealing with a small molecule, and for example, if you didn't have that metal atom there, then how would you be able to overcome the phase problem?
Thankfully, there's a lot of different solution methods. So one thing for proteins that ends up working out well with that. So what you described, that heavy atom replacement, where you replace a sulfur with a selenium, that uses something called the heavy atom approximation, where you can find really easily where your heavy atoms are. And from there, because those are the highest intensity peaks. And then from there, you can go ahead and say, okay, so this spot to this spot, then that should correspond to the relative intensities and phases of the peaks. Okay, this is probably this atom. That's something called the Patterson method. And it can get very complicated very fast based on the number of atoms you have. There's another thing called structure replacement, where there's a structure that's already known, and it's really similar to what you have. So you just throw it in there and then just start modifying it, because from there, okay, this gives a good enough picture of the phases. Now let's just start tweaking it, doing little things, and oh, cool, now we've got the correct phases. And then there's another much more in-depth version, aptly called direct methods, which involves a lot of math that I'm not very good at. I have Girolami here actually, so I need to really read up on direct methods too. But there's a lot of different approaches to being able to solve the phase problem. And thankfully now, mostly this program takes care of it. So this is a program called OLEX. OLEX is a graphical user interface. It's free, thankfully. And it uses this is just basically a GUI. This is just a graphical front end for what the real thing is, which is something called Platon ShellX. ShellX was developed by Dr. Sheldrick a long time ago, still alive, and he still uses his original thing, and he's still updating it. And when he dies, we're screwed. And he's very, very nice. And if you're at an institution, that is also free. You just have to apply for it, but you can get it pretty easily. And those have all of those different phase problems built in. Something called charge flipping, direct methods, Patterson peaks, but you can try all those different phase problem methods directly from the graphical user interface. But very rarely do crystallographers actually go in and do the math anymore. We rely heavily on these programs to do that for us. Because before, doing that amount of math was worth a PhD on its own. And now this is an experiment I can do in that for noon. So technology is great.
Any other questions?
Well, thank you all for your time. And I hope something of that was